problem today is a little bit tricky, but there are a lot of learning and knowledge that we will gain from this exciting problem. The problem is merge k sorted list. So the question is you are given an array of k linked lists. Each linked list is sorted in ascending order. Merge all the linked list into one sorted linked list and return it. So basically, we will have an array of linked lists as an input, and the function or the subroutine should return a reference or a pointer to the head of the joined or the flattened list. We'll see that in a minute in the whiteboard. So here, this is the example. We have here, this is the first linked list, and this is the second linked list, and this is the third. The output is like this. So here the explanation, they say that here, this is the first linked list 1.24, 4.25, and the second linked list 1.23, 3.24, and 2.26. So each linked list separately is sorted, but joined they are not sorted. So here is the challenge. So the output or the end result, we should like somehow try to traverse and sort all of the linked list and join them in one linked list instead of having three linked lists as here in this example. We will join them into one single linked list as here. So here 1.1 and the second 1.22, 2.23, 4, 4, 5 to 6 until the end, which is 6, which is point to null or none in Python. This is the first example. The second example, we have empty list and the output is empty. And the same for the last example. So let's try to visualize this and see how we can tackle this problem and what kind of sorting algorithms that we can reach to. Just give me, guys, 1 minute. I need to grab my coffee. So this is our input. You can see my screen, right, guys? Because sometimes my internet is tripping and
Yes, we
we're
can see
silent.
it.
There were no any kind of interaction. Okay, nice. So this is our input as per the previous example, and this is the output, which is here we have three linked lists. This is the first linked list, which is index 0, and this is the second index 1, and this is the third index 2. And the output we have them joined. So if we wanted to visualize this input, we can see it like this. So here, this is our first linked list. We have here the first node, and it has a pointer to the next node in the list, which one? Here 1.24. So here 1.4 and 4.25. And 5, since 5 is the tail of the list, 5.2 null. So this is the first linked list in our list. Let's go to the second one, which has the index 1, which is here 1, 3, 4. So the head is 1, and it points to 3, and 3 points to 4. Let's 4. There's there's a little bit of noise. There's someone in the street, I think. So if you don't mind, can you just mute your mic? Uh, and here, since 4 is the tail of the list, 4 points to null. And the same thing applies to the last item in the last item in our array, which is the last linked list. And as you can see here, each linked list has a different size. So it just happened to have the first one and the second one has the same size, but the third one, the size of it is 2. So this one, the size of it is 3 element. And the second one also, it has 3 element. But the third or the last linked list, it has only 2 nodes or 2 elements, which is 2, pointer to 6, 6, the tail, point to null. So up to this point, is the images clear?
I believe so. Yes.
Okay, nice. So now we need a way. We have we are given something which is each linked list separately or in turn is sorted. So as you can see here, the first linked list by itself is sorted, and the second one as well. So each separate list is sorted. But the thing is, we need to have them all joined together or flattened together in one linked list, and it has to be sorted. So we need a way to join all of these linked lists in one linked list. So instead of having 3 linked lists, we need to have one list. In other words, instead of having 3 heads, so this is the head, the first linked list, and this is the head of the second linked list, and this is the head of the third linked list. So we need to join them in one linked list with only one head and one tail. So any suggestion, any kind of idea about how to go about this? Or if you have any question, or what do you think up to this point?
Maybe we could recursively sort them and then link it together, starting, for example, from the first one, and we
Uh,
look through the rest of the lists until we find maybe something that is higher or like a value that is higher, and we keep going.
um, go through them recursively, you mean? Uh, can you tell me more about this? Like
I
right
mean,
now we have the biggest array, and each item in the array within itself is a list. So each item is a list. Like you can think of a list as something going down. So this is the first item, and this is the second item in itself is a linked list, and so on and so forth. So to go recursively,
I mean, it's
Uh,
just an idea. I'm not sure. Go on.
I think maybe we merge two lists at a time. So no matter how many lists we have, we merge two lists,
mhm.
and this way we make sure that merge two lists into one list, and then keep going another list with like the merged list.
Okay, we need to merge them in one list.
Yeah, I
Nice.
understand this, but it's like you said, you have like three lists right now. So what if we merged the first two lists together into one bigger list? So right now we only have two lists that need to be merged, and then we
Hmm.
merge the two lists left. So we merge
So,
145 and 134
mhm, mhm.
into it will be. Are we allowing duplicate or not? Sorry, but
So if I understand you correctly, what you've said is we have this list, and then this one we merge them together in one list. Then
yes,
if there is any other left list, we merge this join of the last
yes.
with the last list.
With
Now we
what's
have,
left.
yeah, now we have the 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 flattened list. Okay, this is nice. Nice. So first things first, we need to flatten these lists. So before we can think on how we can sort them together, we need a way to flatten them together. As someone here mentioned. So first, we need to flatten. I don't want to spoil it. Wait. Sorry guys, I'm typing with my touchpad and it's a little bit cumbersome. So my typing is ugly and slow. So just bear with me. So first, I said we need to flatten the list. Uh-huh. Now let's assume that everything went fine and we have flattened the list. We have flattened all the linked list in one list. So how to go about sorting them? What do you think? What is the appropriate sorting algorithm that would be a great candidate to?
Some sort of bubble sort, maybe? Of switching the elements of the list.
Okay, bubble sort. Um, bubble sort. Um, do you know the time complexity of bubble sort? Like, why you choose bubble sort?
Not sure, first one that came to mind.
Yeah, no, no worries. Yeah, just like try to speak your own mind, so that we maybe bubble sort can be uh, a great solution here. Who knows? But first, we need to discuss this in terms of time complexity and space complexity.
No, I
And
think for bubble sort is out of the question because it will really take a long time for that to be sorted because now you're looking at appending the list because you're creating a new list when you're actually sorting these linked lists. So I'm not sure whether bubble sort will work, but I would say it would really not be efficient in terms of time complexities.
Okay,
can you
so I think
remind me what is the
the
time complexity of the bubble sort,
I think it's n
since that
squared,
you
two of
said
n
it is
squared.
very slow?
Can you hear me? Hello,
Hello?
can you
Hello?
hear me?
Yes?
Yeah, I think for bubble sorts, the time complexity is approaches O of n squared.
Uh, excuse me, sir. Your voice was breaking.
Okay, is it better now?
Yes, yes.
Okay, I said for bubble sorts, the time
Mm-hmm.
complexity approaches O of n squared.
Okay, O of n squared. This is the time. And what about the space complexity, which is how much of the memory the bubble sort utilize or use?
Okay, for bubble sorts,
I think O of one. I think if I'm wrong, please someone can just correct me. So bubble sort is
okay,
O
so
of n squared.
usually for
So
sorting
so
algorithms,
if
the
we have
space complexity is usually O, right?
mhm, yes, so we need actually here to discuss both of them, the space and the time, because sometimes you might be working on a machine that with very limited resources. So you might choose uh, a great and blazingly fast algorithm, but this algorithm might use a huge portion of the memory. And since that you are in a very limited machine, so you are not gonna, this algorithm will not be any kind of useful to you because the memory concern. So bubble sort is very slow, as you said. What else? What kind of sorting algorithm we can use else? So if we put them here, the algo and time. and space. So Sabah suggested bubble, and someone commented out that it is O of n squared very slow, and it doesn't utilize much of the machine space. I think it is all one. So what else sorting algorithm that we can use here, guys, other than the bubble sort?
Uh, may I say something? Why are we needing sort? Because are we gonna change? It's gonna end up as a linked list, right?
Okay,
We're
this is
gonna
a
end
great
with a linked
this
list,
is
even if we merge it.
this is
Let's
a great
say
question.
let's make it
So
look like just two linked lists. We're trying to merge two linked lists together right now. So we already have the
mm,
location of each node. So what we
mhm,
need to compare is the two node. So
okay,
which one will come first, and that will be, and we will add it to the location for the new node, for the new linked list we're gonna create, or
which one come first?
we will
Can
just
you
point to
elaborate
it.
on that? Can you elaborate on that much more? When you
Okay,
say
so
since each one
we
come
have
first.
the head of the first linked list, let's say one, and the head of
Okay,
the
this one.
second linked list, let's say it's okay. I cannot see it exactly. So
Here,
we
here.
have
This
one
is the
and one.
first one. This is the second. This is the
Yeah.
third.
So
Huh?
that was my question. Are we giving duplicate or not?
Yes, we are given duplicate, and we might have
I
thousands of
understand that, but
linked
in
lists.
in our final linked list, can you show me
Yes,
the output? Will it have the
yes, of course, we
duplicate?
might have duplicate. Yes, here one is
Okay, so
duplicated,
basically,
or is
I just
duplicated.
I compare the two of them. If one of them, if they are equal, I just take one of them, and and the other one. If they're equal, it's the next. I make the next pointer point to the head of them. Then I just keep referencing the next and compare them. I
Keep
just need
in
to
mind,
compare two nodes together.
okay, keep in mind that,
I don't need to sort. I
okay,
don't think I need to sort them because they are already sorted. So I only need to
no,
compare where I
they,
am.
okay,
No, but remember that there are
half,
three linked
you are
lists
half
here. We're not
true.
comparing two linked lists. You can't be. I understand what you're saying, but it's invalid because there are three linked lists. So are you saying that we're going through linked list number one, linked list number two, and then merging that, and then what about linked list number three?
Yeah, that was my idea. I'm not doing them as like I am not comparing all of the linked lists together. What I am
Yes.
suggesting is a function that merge only
Yeah.
two linked lists together, and another
Okay.
function that
Okay.
I already
Okay.
have this merged linked
Okay.
list.
Okay. Yes, we understand what you mean, but remember that's why Abdallah was speaking about time complexity. You remember that? No, no, I'm in class. I'm in class.
Uh, okay, what's your name? Uh, was the speaker? Okay. Uh, so what you are saying is we don't need to sort them. So you are half true and half wrong. So what you've said, which is we already have, is we have them sorted, but separately. Each list separately sorted. So like the first list by itself is sorted. So we have the head one, the next node is four, the next node is five. And the same thing applies to the other list. But we won't join them in one huge list. But when we join them, we need to compare, like maybe we have 10 lists, like 10 different lists. We have 10,000 different lists. Maybe we have million different linked lists. So how we need a way to compare them so that the end result is one flattened sorted linked list. So we need to sort them. When we join them together, we need to sort them. So this
I
is why
believe
we are discussing
I believe
which
we
which
have
is
Well,
the
well,
better way.
different ideas.
I
One is flattening everything and then sorting the unsorted list. And the second one, that's Mana's idea, is going list by list. So you always keep your list sorted. So you have the first one sorted, and then you add to it the second list, and you keep it sorted, and you go on. I mean, it would be
Mhm.
good to explore both, but we can go with the one that is most effective and efficient.
So Sabah, you are saying
I've got another one, but I'm not really sure because I joined late, so I'm not sure about the givens. But I thought about something at the beginning that if I notice in the output that they are stored, I'm not sure if this will be the given all the time. Please correct me. So I'm thinking that we if we have three linked lists, so maybe we have a dictionary of three, which basically or any data structure that will keep us going. Have a pointer to the next pointer or the current pointer in each level. So we have a pointer like we have a data structure that and at the meantime it has if not null, at least it is gonna like if we could start from 1 1 2 and the next time so we sort them somehow and then we add them like in a sorted way and then the next time iteration so to speak we may have 4 3 4 sort like add them in the sorted order. Is that you think this could be a valid point?
Yes,
And
actually,
again
creating a new list. Yes, creating a new list will work.
yes.
just
So
tell me am I understanding correctly because I didn't got from the beginning. I thought I got misleaded. So any
Can we
clues,
can
guys?
we can we go through all the lists and make an array, then sort it, then make a new list?
yes. So we are here in this phase, which is we have gone through all the list some way somehow, and we managed to flatten it. But the question was, guys, how which kind of sorting algorithm we need to reach to, if you get me. So let's say that, guys, we solve the first stage or the first part, which is we loop through by some way we loop through all of the linked list and we put them in one flattened list. So some of you here suggested that we need, for example, we need to loop through the first list, then join it with the second list, then sort them, then go then we carry on with us the joint of the two lists and they are sorted and we join them again with the next list and we repeat the same kind of process.
But
Can I say something?
can we why we don't
I,
have an array? Put all the values of each node in that array, and then sort that array, and then make another linked list. I think that's better than dealing with lists. Are
Okay, guys.
Yeah, I think what Abdullah is looking for is the algorithm. So I don't like we're all circling around the same thing that we've been saying for the past 2 minutes. I think what Abdullah is looking for is the algorithm. I don't know. In my mind, I'm just thinking about merge and sort variation or multi-way merge. I don't know. I'm just throwing it to the floor so that like we just conclude because we're saying one and the same thing that it's obvious that we have to create a new list and all that. So like let's speak about the algorithm.
Yes, okay. Let's speak about the algorithm. So
I think
we have
the
variations of algorithms we
the
have.
quick sort.
For
I
example,
think
we
it's
have
like in login, right?
so for the O of n squared, we have insertion, we have selection, and all of them share the same kind of time complexity and the same space complexity. And all of them they are pretty much they are relatively slow compared to the next algorithm, which are we have merge sort. We have merge sort, which is if I'm wrong, please someone correct me. N log n, and the space complexity it is O of n, I think, and we have quicksort. We have the quicksort. And the space complexity of quicksort, I think, is the blazingly fast log n. But in
No, I
the
think
worst
it's
case,
n log n.
no, quicksort log n,
Yeah,
n
n
log n.
log n,
Are you
right?
No, n
are
log
you
n,
sure?
right? Yeah,
Yeah.
Can you check on that? N log n or log n? Quicksort
n log n, right?
n log n.
Is a certain algorithm. It's not possible to sort something in log n time.
Okay, my bad. N log n. And for the space complexity due to the stack frames, I think it is also of n. And we have heap sort. We have heap. And heap is O of n log n also. And the space complexity or the memory, in the worst case, it will take log n, which is the height of our tree. So among these algorithms, we can exclude the slowest one, which are the bubble and the insertion and the selection. And we are now left with the fastest. So we can go with merge, can go with quicksort, we can go with heap sort. But there is some downside of using quicksort here. Even though the quicksort is the fastest one here, I just need to check something, guys, because quick quicksort. Best case n log n, yeah. Base complexity auxiliary all log n. One of the downside of using quicksort is that if we have some part of the list already sorted, then we will fall into the worst case of using quicksort, which is of n squared. This is the very worst case of quicksort, and it is very rare to happen. But when the list is already sorted, quicksort is not a good choice. It's a very bad choice. And since that we expect, we ex not we yes we expect each list separately will be sorted, then we can exclude quicksort from here. And now we are left with merge sort and heap sort. And I do think the merge sort it uses much of the memory because of the copying. We need to copy for each level of the swap. We need to copy. So the choice here that we are left with is the heap data structure or the heap sort, which is a kind of a kind of implicit data structure. And what does this supposed to mean? Implicit data structure, which is it means that we don't need extra space to represent this data structure. We only just
Sorry, Abdallah, can I ask a question?
yes.
But if we're speaking about the heap sorting algorithm, isn't it suited for, like an array of I would say a single array of elements to sort.
An array of what? Come again?
A single array of elements to sort.
Single array of element. Yes. Yeah, you mean one dimensional array? Or what do you mean by single array?
Yeah, like I don't know. Like I think it's okay. Of course, yeah, we've been merging all of them, all of the three
Yes.
linked lists. But
Yes, I need to merge them.
um,
Yeah.
yeah, it is just a question. Actually, I'm just thinking.
Yeah. Actually, for this kind of problem, both both merge sort and heap sort, they will be a great candidate. But for the merge sort, since it utilizes much more of the memory, and sometimes you are so limited to the machine resources, so I do think it is much better to reach for algorithm that doesn't use much of the space. And since the heap is an implicit data structure, and as we've said previously, implicit data structure is a data structure that doesn't have a representation on the memory other than the original data structure, which is could be array, could be a linked list, whatever. And it is very easy to build heap data structure out of an array. So this is the idea of implicit data structure. So like for the linked list, we have here, as we have represented here, this is a node and a pointer to next node, pointer to next. So linked list, it has its own representation and it consumes a decent amount of memory. But for the heap, it is implicit. It doesn't need its own representation on the memory. The second property of the heap data structure, it has to be complete tree. So if you can recall from the module on Alex of the tree, like a tree, it's said to be complete binary tree when each level of the tree is filled or fulfilled, except except the last level, and it has to be inclined to the left. So we fill from left, then going right, left going right. So as a quick example, if we have, let's say this is a tree. So this is complete binary tree. And this is also tree with only one node, complete binary tree. But this one is not considered complete binary tree because, as we've said, uh, each level is fulfilled except the last one, and each node, all the nodes should be inclined toward the left. But this one here is skewed toward the right. So this is not also completely complete binary tree. But if we take another example, this is complete binary tree. This is also complete binary tree. Because all of the nodes are like are farther to the left. Like the last level is further to the left. So this is the features, or this is the characteristics of the complete binary tree. And why the heap should be complete binary tree, we'll see that later. One of the downside of the heap data structure is that it is not stable. So stability, when in terms of algorithms, when I say this algorithm is stable or not, if we take here, for example, if we take our input and the end result, we have 1, 1, 2, 3. So the stable algorithm states that if this one in the first list comes before this one in the second list, the output also will have the one that comes first also comes first in the output. Did you get the idea of stability? Like, yeah, it doesn't matter if we have this one first or this one first, but sometimes in some sense, for some reasons beyond the scope of this question, uh, we might come into a circumstance where we need an algorithm that is stable, that preserve the order of the elements. Did you get the idea, guys? Or I'm just talking the talk?
Yeah, it's clear, bro. Continue.
This is the idea of stability when we talk about algorithm. And for the time complexity, it is n log n. So why it is n log n? So first, I need um, I need to build I need to build the heap. I need to build the heap, and building a heap data structure requires O of n. Secondly, I need to heapify and sift down, which is sorting the heap, and the sort requires log n. So those combine together, O n log n. And for the space here represents the height of the tree. The height of the tree. So the worst case scenario, I need to traverse the whole height of the tree, which is O log n. Because since it is a complete tree and the height of complete binary tree is O log n. So these are the fundamentals of our chosen uh, algorithms to go about this problem to solve. So up to this point, any question or any blurry image, something? And why we choose algorithm from one another? Hello?
Yeah, seems straightforward so far.
I think it's clear to me. Well,
Okay.
since you raised the opportunity for questions, I have a question because I'm not gonna be able to get in the end. So I hope that if we have time at the end, you try to criticize the solution I came up with and tell me why whether it's right or wrong, and if it's wrong, why. Which, as I said, you won't you will traverse levels, so you will keep it as a linked list. You will traverse level by level, so you'll as if you go back, please, to like go to that painting yeah, just to the left, a little bit to the left, yeah, this linked list here that
Yeah.
you draw. So I was thinking, go level by level and sort every level and add it to a list. So incrementally, you're adding elements with the right order. So if you can please, if you had time at the
So
end, please criticize the solution.
okay. Who am I to criticize it? Like maybe it is a great idea. Like
Yeah, I mean, like, I like
I'm not saying it is
discuss it or
a
see.
bad idea. I'm not saying that this is bad idea. Maybe it is a great idea.
Roughly, yeah.
Okay.
Thank
We
you.
can discuss it. We can discuss that. We can discuss that. No worries.
Okay.
So let's go to our pseudo. So, so first we said that we need to flatten the array of linked list, and second we need to build our heap. Build our heap. And I think Ernest has said something moments ago that that is related to heap sort only operates on single element array or something. So since that we have flattened our array, I think we will have one dimensional array, and we can like easily build we can easily build heap data structure. And third, after we build our heap, we need to sort the heap. Sort our heap. And it's very messy. Fourth, since that we are operating on linked list, not only just single element, like we are operating on object. So we need a way to break the link of these. And like, let's say, for example, the one should point to this one instead of 4, and the next one should point to 2 instead of 6. Like, we need a way to adjust the linking between, adjust the linking among these linked lists. So we can say for we need to build or adjust our linking, adjust links in singly linked list. What's this? SLL, singly linked list. And after we adjust the link, last but not least, return head. We need to return our head. This is our head. We need to return. Yeah, so for these steps, is it clear? Like, just from a bird's eye view perspective, like this is a very general view, or like as the helicopter's view or something. So is these steps are clear? We need to flatten it. We need to build our heap. We need to sort our heap. We need to adjust our link. We need to adjust the link of the single link list. Then we just need to return a pointer to the head of the new adjusted linked list. I think I made it more complicated, right? Yeah, actually, it is kind of complicated. So, guys, let's say that after we have flattened the list, let's expand on this pseudocode. Let's say that after we have flattened our list, we have this result. We have here the green. We have 1, 4, 5, 1, 3, 4, and the last list 2, 6. So this is our flattened list. This is our flattened list, or this is our joined list. So we need to build a heap out of that, and there's important thing that I meant to mention, which is how does the heap operate and how to build a heap. So basically, we have two kind of heap. We have two kind of heap. So we have min heap, and we have max heap. Min and max. And both of them, like they say that whenever you are in an interview and there is the topic of the heap data structure, you need to mention priority queue, because this is how people on the market and on the wide they call it priority queue, and this is one of the major use cases for heap. It is used on priority queue. And what is priority queue means? Let's say that I have a collection of data, and let's say I need the most visited or the most frequently visited data. Let's say for example, so the most visited kind of, let's say we have a profile on social media, and I do want the most visited profile on this social media. Let's say it is Discord, let's say it is Facebook, whatever. So if I put the collection or the list of profiles on heap, I can easily, if it is on min heap, then the root of the heap will be the least visited profile. And if I have put it on max heap, the root of this heap will be the most visited profile. So in a nutshell, the root of the min heap is the minimum item or the minimum node. So here this is 1, 2, 3. So the root, this is the root node. This is the root. The root is less than its children. And for the max, it is the complete opposite. I should have 3 here, and here 1 and 2. So the root here is the dominant node or the greatest node, the good. So here the root is greater than its children. So these are the two the main kinds of heap, min heap and max heap. And depending on the question on hand, you can decide to either build min or max. And in terms of functionality or in terms of like they don't differ a lot on their implementation. So this is the thing that I missed on, and I missed on, which is explaining the two kind of heap. So is it clear up to this point, the kind of heap, min and max? So going to our example, if we build a max heap or if we build a min heap, we will achieve the same kind of time complexity. So it is just a matter of preference. So let's go to our pseudocode. So up to this point, we are on stage 1. We have flattened the array. Now stage 2, which is we need to build our heap, right? We need to build. So how we can build implicit heap data structure out of an array. So there is some rules we need to follow, which is for each element in the array. So the element at index I, its left child, I can get it by the arithmetic of 2 times I plus 1, and the right child 2 times I plus 2. And if I have a node and I need to get the parent of that node, I just need to get the lower bound of I minus 1 divided by 2, which is the floor. So let's make this more practical. So let's build a heap data structure out of this array. So here, let's first let's highlight our index 0, 1, 2, 3, 4, 5, 6, 7. So we have 8 items in this array. So this is our root 1. This is our root 1. So here I have the rule saying that if I want to get the left child, 2 times I plus 1. 2 times I plus 1, which is 2 times 0, 0, 0 plus 1 is 1. So the left child is 4. The right child, 2 times I, and still I is 0, 2 times I plus 2, which is index 2, which is 5. Now, I need to get to 4, because as we've said, it is a complete binary tree. So like someone might ask why you went to 4 and you didn't go with 5, because it is a complete binary tree. And a complete binary tree, it is filled from left to right, left to right. This is one of the main characteristics of complete binary tree. So I need to get to 4. So 4 here, it has index of 1. So the left child of 4 is 2 times 1 plus 1. So 2 times 1 is 2 plus 1 is 3. So the left child is 1. And the right child, which is 3 plus 1, 4 index, which is value 3. I know that I am going very slow, but like this is the best I could come with, because like there is a lot going on in the, because we have many data structure. We have linked list, we have list, we have a heap. So like just try to bear with me if I'm going slowly. So here we are on 4, and we have constructed its two children. Now move to 5. So 5 index 2, 2 times 2 is 4, 4 plus 1 is 5. So the left child of 5 is 4. And the right child is what? Can anyone help me? What is the right child of node 5? Hello? Hello? Hello?
2 times 2 is 4 plus 2 is 6. So it's 2.
Yeah, understood. Nice. Now we have the last element. So where can I put it? Here or here or here or here?
Domain 1, the most left.
The most left, yes. So here, 6. So now our heap data structure, but it is not yet min or max heap. It is just a tree. Like we need to decide. We need to be a max heap or min heap. And as we've said, the main feature of max heap is the root is always greater than its children, and the min heap is the opposite of that. So I delete this here one to make it more a little bit clearer. So let's say that I want to build a max heap. So in order to build a max heap, I need to start from the bottom. Starting from the bottom now, yeah. So I need to start from the bottom, which is the very leftmost, or the very left leaf node, which is 6. So what I will do next is, can I copy these to any location? Like anyone here is expert with Excalibur. I just need to copy this tree to another place here.
I believe you can choose the cursor up there and just select it.
Nice. Papa عشان so here, and this is bring our array. Here. So we said that we want to build a max heap, which is the property of max heap, the root, like for every single subtree and the main tree, the root has to be greater than its children. So here the root is 1 and its children, both of them are greater. So this tree is violating the rule of max heap. So I need to hold or maintain, or I need to restore the property of the max heap. So what can I do is going to the leftmost leaf node, which is 6, and I need to get its parent. So how can I get a parent of a node? I have here a rule of that. The parent is the lower bound of I, and the lower bound of I minus 1 over 2. So I have 6 here. So the index of 6 is 7. 7 minus 1 over 2, which is 6 divided by 3. So the parent of 6 is 3, as we can see here, is 3. So is the parent, or is the child is greater than the parent? Yes. So I need to swap. So I will swap 6. I need to swap 6 with its parent. So now I will have 1 here and 6 here. My cursor will go from the rightmost, which is which was here in our tree, the leftmost leaf node, and here in our array, it is represented as the rightmost item. My cursor was here. Now my cursor will go here, and I need to get the parent of this node. So the node is 6. 6 minus 1 divided over 2, which is 5 over 2 is 4. So the parent of 2 here, 2, 6, 6 minus 1 is 5, 5 divided by 2 is 2, right? Yeah, 5 divided by 2 is 2, and we have a remainder. So we take the floor, or we take the lower bound. So 5 over 2 is 2, and we have a remainder, blah, 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 but we don't care. We only need the whole number. So the parent of 2 is the item that has the index 2, which is 5, as we can see here in our binary tree. Here is 5. So does the child is greater than its parent? No. So up to this point, the heap property is met. So my cursor was here, then it will go to the next. As you can see, we are going from right to left. So here I am on node 4 that hold the index 5. So I need to substitute the same rule. 5 minus 1 divided by 2, which is also 4 over 2 is 2. So here 4 is greater. So here the parent of 4 is this element, which has the index 2. And we can confirm this from the looking of this tree. So 4 is greater than 5. No, the heap tree is still, the property is still met. So my cursor will move next,
I
which
have
is
a
to 3.
question, please. Sorry to interrupt.
Yeah.
Why are we trying to make a max heap tree when we're trying to have our list be in ascending order? Shouldn't we be trying to make a minimum or a heap tree?
Yes, you are right. This is very good question, by the way, Salah. It's a great question, but we'll see later. It doesn't make any big difference if we build min or max, and we will see. We will see. But your question is a great question, by the way.
All right.
So because it does make sense if we just build a min heap, we can just then pop up the root, right? Because since the min heap it maintains the least item on top, which is the root, can just each time I can just pop the root. Then I need a way to sift down, go up, get. But since okay, I will discuss it right now. Since let's say that we are going with the min heap, and now I have already the min heap or the minimum item as my root, which is 1. So now I need to pop this item. Okay, I pop it and I put it in a container. Let's say the container is just a list. Then what can I do next? Like now my heap is messy. I need my substitution of that popped of that let's call it of that guys, come on please, I lost the word. Yeah, the root. So who is going to replace the previous, like who's going to be the successor of this popped root? So I need to make operation of sifting down and going up in order to have a successor of this root. And since for the min and the max, we both will do the sifting. So this is why I said it doesn't make any big difference going with min or max.
I mean, if we
So
went with
let's
min and
left
we
off.
instead of
Let's pick up from where we left off. So here we are on 4. Element at index 4. Um, what I want to do? Yeah. So I need to its parent. So 4 minus 1 is 3. 3 divided by 2 is 1. So 3. So the parent of 3 is the element at index 1, which is 4. So 3 is greater than 4. No, the heap property is still maintained. Now my cursor will go next. Now I'm here, 1, which is hold the index 3. 3 minus 1 over 2, which is 2 over 2 is 1. So the parent of 1 is 1, where actually we have changed that since we made the switch. We didn't update that. Yeah, we should have updated that. So this one should be 6 because as you remember, guys, in the beginning we have a switch between the 1 and 6. So now we have 6. So 6, the parent of 6, which is 6 at index 3. 3 minus 1 is 2. 2 over 2 is 1. So the parent of 6 is the element that lives at index 1, which is 4. So 6 is greater than 4. As we can see here from the looking of this tree, the heap property is violated again. Now I need to do the switch. I need to switch between 6 and 4. So here I will delete this and this, and I will have my 6 here and 4 here. And now I need to update this as well. Here I have 4. Here is the 4, and here is the 6. So since that I have made the switch, I need to go next. So my cursor was here at index 3. I need to go to the next one, which is index 2. So element at index 2, its parent is 1. As we can see here, 5 and 1. So 5 is greater than its parent. So the heap property is violated. Now I need to switch between 5, or I need to swap 5 and 1. So here I need to delete the 5 and 1. I need to have the 5 and here the 1. And now my cursor is here. And I need to update this as well. Here 1 and 5. 1 and 5. Now my cursor is here at 6. So 6, its parent is 1 minus 1 minus 1 is what? Is 0, 0 divided 0 over 2 is 0. So the parent of 6 is 5, and we confirm this from the looking of this tree. So 6 is greater than its parent. Heap property is violated. I need to swap. And this is only one round of heap, and I need to repeat the same kind of thing until my heap is empty. And I think we are done with only one round because it is very tedious. I need to swap here. By the way, guys, the implementation is very simple, but the understanding it's a little bit trickier for me at least. We swap the 6 and 5, yeah. So the 5 here and the 6 here. So now we have this one left 5 and 6. Now we have the biggest item at the root. And what will be next is I need to swap between the first element and the last element. And when I do this, the 6 will get here and the 1 will be here. Now, from now on, I will repeat the same kind of processes, but the last element will be executed. So my new tree will start from index 6, which is from here. Did you get the idea, guys?
Yeah, it
I
does
will
make
keep
sense.
repeating this until all my array are sorted. And keep in mind that this is not linear. Like you might fall victim into the fallacy that this is look similar to selection sort, because I am looking for the biggest item and then throw it at the end and repeat the same process. But I'm not going linear. I'm going logarithmically, which is here, going by factor of 2 here, as you can see. Each time I go by 2 times I plus 1 or 2 times I plus 2. I don't go linearly. I go logarithmically. So did you get the idea, guys? This is the whole this is the idea of it. Is it clear?
Yeah, it is.
Is it clear, or I just made it more complicated? Hello?
Yes, it makes sense.
Where is the list? Yeah, here. Hello, guys? Hello? Can you hear me?
Yes, I said it
Am I
was
off?
clear.
Hello? Hello? Hello, 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 hello,
Hello?
hello.
No, you're not off. You're not off. I can hear you.
Yeah,
Just trying to wrap my head around this.
yeah. So up to this point, do you have any question? So we'll be repeating the same processes until we have our array fully sorted. And the next time we'll have the 5 here, and our new array will start from this point, and then this point up until we have only one array with one item, and now we are finished. Our heap is sorted, our array is sorted, everyone is happy, the checker is tremendously excited.
Okay, so I have a question because you created a heap then you were still referencing the linked list. Is it that in the heap, each of the node in the heap also has a pointer to the linked
Yes,
list?
yes, this is a great question. Now, we have sorted our list, but we did not adjust our linking. Still, the linking are missed. We have sorted our heap. Now we need to adjust our linking. So how we can do this?
Can we not switch
Any idea?
the elements as we go
Like we have
instead of
sorted our list. Yeah, we have used our lovely heap data structure. We have sorted in logarithmic time complexity, and we haven't consumed any memory since the heap is implicit data structure. Now, how we can maintain the right linking? The right linking.
Can we not switch elements as we go, making up the links as we go?
Sorry, can you explain the linking? Because that's where I'm getting cut off here.
Come again? Hello?
Yeah, I can hear you. I just wanted you to explain the linking. Is it that when you are creating the heap data structure, you're not creating any memory? Each node has a pointer to the given flat, right?
I don't know. There is a buzzing voice. I couldn't tell. Sorry.
Okay, can you hear me?
Yes.
Hello. Okay, so I was asking the data structure, the heap data structure. I just want to be clear.
Mhm.
Each node in the data structure has a pointer to the given linked list, the flattened list, right?
Yeah, up to this point, we haven't discussed about how we can how we can restore or how we can adjust the link according to our sorting. We haven't discussed this yet. This is the elephant in the room.
Wouldn't it be smarter to
Okay,
switch the
okay.
links as we go instead of just switching positions and then going back again and switching the links?
Come again, Sawa?
I said, how about switching elements with links as we go instead of leaving them till the end?
Yes,
So when switching one and
it's a
six,
great idea.
you also switch their
Yes,
linking.
yes, yes. This might be a neat idea, but bear in mind that if uh, what you're saying is that as I go, as I go, I'm swapping and switching or adjusting the link at the same time, right?
Yes.
If I understand you correctly.
So when switching one and six, for example, then six or like one would have the null as the next, and two would have one as the next, and then six would have four as the next, instead of just switching positions in an array and just leaving it till the end.
Yes, this is a great. And actually, if we implement a min, if we implemented a min heap, this would be much more easier to adjust the link as well. Like we can adjust the link and swap the element as we go at the same time. So yeah, I think that that is all to it. Oof. Any any question? So here, let's revise our steps again one more time. We flatten our array, we build our heap, we sort the heap, we adjust either at the end or as we go, and finally we just return pointer to the head. Can we give it a go?
Yeah, sounds good.
Let's give it a go. Let's give it a go. Where was it? Where- Like all of my tabs are heap, 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 heap. Um, Here, yeah. So I'm just gonna switch to my text editor because I'm more comfortable with it, and then we can migrate that again. So we can start first. We need to where's the whiteboard. First, we need to flatten our list. So we can just make a simple loop. So for node in list, this list right is with S for node in list, and I need to have list of linked list initialized with empty array. Then since each item in my list each item is the linked list as well, so I need to go through the linked list as well. So while node my list of linked list dot append node uh, no I. So up to this point, let's say I have a list of two linked lists. So the node here, it will hold the head of the first list. Then I need to go through this list. So in order to go through it, then node equal node dot next, right? Because it's a linked list. And this is the prototype. It has a value and next. Node equal node next. While there is a node, then I will append all of the element of the list on hand. And when I reach null, then this is the point where I will move to the next linked list. You get it? So here we are flattening the list.
And are
Now we
we
need to do what?
connecting the list somehow?
No, we are not connecting.
Why not?
We we are not. We will connect after we sort. Do you have any great idea to do it while we are flattening the list? Because
I mean,
the
you're
time that I need to at the time that I need to link them is when they are sorted. But right now they're not sorted. I have just flattened them. Like this here. Where is it? Where is it? Where is the flattened example? I have just made the list like to look like this one. It's just one list. But the link up to this point are messy. The link are like they are messy.
oh yeah, gotcha. Go move on.
So the next phase is because how can I link them and I didn't solve them yet? Because I don't care about their previous linking because it doesn't make any good for me to solve the problem. I need to sort them. Then according to the sorting, I need to adjust the links. So the next phase is I need to build my heap. So any idea about building the heap? as we have said here, we have here we have first, last, and such. So basically, if we follow Wikipedia for how to implement heap data structure, we'll find that a heap it has two main subroutines. We have the sift down and we have the heapify. So the heapify is to maintain the heap property, and the sift down is to go either sift down for the top down heap or sift up for bottom up heap. So a sift down and up is for traversing, and the heapify for maintaining the heap property. The pseudocode for this in Wikipedia, they provide like very comprehensive pseudocode and a lot of variations. So you can refer to that later. So now I need to build my heap. So how can I go about this? I need to get the size of my list, which is len of list. And I need to build my heap. So how did we build it here? We have our array, and we went from the very rightmost, like our cursor started here from right, then we advance left, 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 right? So let's declare our iterator I equal size -1 here, because we need to start from the last element in our list, right? We started from here, remember? Like we get the parent of this and such and blah, blah, blah. So while I less than or equal 0, because here I have my cursor, I move forward until I reach the very, very first item, then I swap, then I repeat the same idea. So while I greater than or equal to 0, I need to do what? I self.heapify, and I need to give it my list, and I need to give it my current cursor, which is yeah, the current node and the size. I need to indent this, and I haven't implemented this yet, but I will do. So in heapify we'll do what we'll do. We will check the left and the right child for the item on question. And how can I get the item on question? Through this I. I have here I have started I by size -1, which is the index of the last element, and I have my size to not go beyond the border of my array or my list. So here I build the heap, and heapify self and it trouble, and I have my I and size. Heapify max heap sift down يبقى fine and save down. And save down as well. So what we have done here, we have our last element at index 7. We get its parent, right? So the parent of 1 was what? Parent of 1, 7 minus 1, which is the formula to get the parent. 7 minus 1 over 2, which is 3. So the parent of 1 lives at index 3, which is 4. 1, parent 4. We confirm this from the looking. So I need to get the parent, and I need to get the left and the child. So I need the index of parent, or let's assume that the index of the large item is the root itself. Let's assume that the root is the largest one. And I need to get the index of the left child, which is the index of the left child, which is 2 times I plus 1. And for the right, 2 times I plus 2. So now I have the left and the right, and now I need to compare. Is my right child and left child greater than my parent? And if so, this means the heap property is violated and I need to swap. So are you following along, guys?
Yes. But aren't we doing um something not
Max
similar to
here?
what we discussed earlier? Because
Yeah, yeah.
the way we did it was we starting from the leaf and then going back to the parent. But here it's almost like E is the actual
Y-
root. So for example, if we're starting from index 7, which is 1, you're looking for the children of 1 instead of the parent of 1.
Yeah, you are right. I need to get the parent. I need to get the parent. I parent. I parent, which is
So floor of E
uh,
minus 1
I minus I minus 1,
time or
right?
divided by 2. Yeah.
So, like this. Like this, yeah. So now I need to compare. So let's say that the largest uh, here, the largest is I parent. Let's assume that it is already the largest. Now I need to confirm this. So if the index left less than my size, I'm not going beyond the border of my list, and my iterable of I left is greater than my iterable of I largest, then I need to adjust my largest. Then then the index of largest is the index of left child. And I need to do the same for the right. Right. Here. Right. You get this? So up to this point, I need to determine which one is the largest. Which one is the largest? The left child or the right child? And if my largest is not root, if I not equal I largest, which is my root is not the largest, I need to swap, and I need to swap the I and the largest, regardless if the largest is the left or the right. I don't know from the code, but I've already determined which one is the largest. So here I have determined which one is the largest. Now I need to swap between the root and between uh, the root
I
and
believe
the
I believe in this
children.
case we're starting from the top of the tree, not the bottom, maybe. Since we are checking
Come
the
again?
root first. I said I believe in this way we're starting from the top of the tree, not the bottom. And if we're doing it this way, then the E large should be E instead of E parent.
We are starting from the top of the tree,
Yeah,
not the bottom.
yeah, because for example, if you check
Mhm.
one, which was the root of this tree, you check it for its two children, and if one of them is bigger than one, then
No, no,
you switch it.
I get the parent of one.
But that
I
is
get
not
the
what
parent
we're
of one.
doing with the code. We're checking the
Uh,
children instead of the parent.
uh-huh. Yeah, yeah. You mean like this, right? Should be I if I of parent not equal I of largest, right?
Yes, but I'm not sure. Because if we're checking the children, I believe we shouldn't check the parent. Or if we're checking the parents, then we shouldn't be checking the children.
If we check in the parent, we shouldn't be checking. We have get the parent. We have get the parent of one.
Hmm?
Okay. Now, uh,
But in the code, you're checking the children of one,
uh
which is null and
yeah,
null.
yeah, yeah, yeah. You're right. You're right.
We can code what we
So
explained earlier. So you check if
we
E
can
is
do it.
bigger than parent, and then just switch with that.
Okay. Why not? Why not start from there? Like we can start from. We can start from here, and then our previous code would be valid. Like let's say if we start from here, from the middle, like here. Let's say I is uh, size minus one. No, size divided by 2 minus 1. So I start from the middle, okay? And while I'm not ensuring not I'm not going beyond the border of my array, then I don't need the parent. I only need the I here, and everything is legit, right?
Yeah, sure.
Right. So here now I need to swap because one of the children is violating the heap property. So swapping in Python is very easy. Like I can say trouble of I, the trouble of I large equal, and here I need get this at the beginning. And now I have swapped them. And since that I have swapped them, I need to do what? I need to move. Like now, we just made a little adjustment. So instead of starting from the very end, we have started from here. So our size right now is 8. 8 divided by 2 is 4. 4 minus 1 is 3. So 0, 0, 1, 2, 3. I will start from here. And we are moving backward. So our bookkeeping, this is the bookkeeping, which is our iterator, I minus 1. Do not go infinitely inside this loop. So we are checking this element, and so 4. So we have 4 here. So for the 4, do we have, we only have left child, but we don't have right child. So is the left child of 4, which is 1, violating the heap property? No. Then we move from 2, we move to 1. So 1 here we have 5, and we repeat. You get the idea? Like we just made a little change, just little change. You get the idea, guys?
Yeah, yeah.
Previously,
Yes.
we started from here. Right now, we just started from the middle.
Yes.
You know, because if we made it from here, the code will be a little bit long-winded, and like it might have some like long-winded, and maybe we don't need to start from here actually, because they are this is already leaf node. So like leaf node, they don't have children. So it makes more sense to start from the middle. So this is just the adjustment that was inspired by Salah. So let's continue. Now we check 1 is greater than 4. No, the max heap property is still maintained. So my iterator will go from where I have started from 3. Here I have started, I will go to 2. So 2 is 3, 2 is 1. So 1, it doesn't have children. Now I go to 5. So 5 here, I check its children. And if any of it, like this is the sorted one. This is not the original list. So just let's keep going. The thing that I want to highlight after we find element that is larger than the the root, I need to switch them. Now I need to sift. Sift means like I need to either go down or up. So I need to sift. I can just recursively, I can make another subroutine, which is sift, for example, sift down or sift up function, and then give it the array and such. But we can just simplify this by calling our heapify recursively. So I can say self.heapify, and I give it my iterable, but this time I will sift by the I largest, because this is where the heap property was violated. I large and the size. So up to this point, this is the idea of heapify. Is the idea of recursion here is clear? Why we did this? Like, where was the original array? Where was the original array? Like I lost it. This is the sorted one, right?
I guess you can get it from the LeetCode.
You can get what?
You can
Okay,
get
okay,
the original list from the LeetCode.
okay. I think we have it here. Here, yeah. So we have 1, 4, 5, 1, 3, 4, 2, 6. This is our flattened list, right? And the way we have built our heap, where is the cursor? We have the root 1, left 4, right is 5, and 4 has 1 and 3. 0, 1, 2, 3, 4, 5, 6, 7. So 4, it has 1 and 3, 1 and 3, and 5 has, this is 3, right? 4 and 3, 4 and 3, and last but not least, we have 6 here. So this is our complete tree. And we said that we started from index here, size 8 by 2, which is 4 minus 1, 3. We started here at 1, which is here. We started here in this one. And we check for the 1. Does one of its children greater than it? And if so, here we have swap them. And after swapping, the 6 gets here, and the 1 gets here. And then we sift down by the 6. And since now the 6 is the leaf node and it doesn't have any node, then the recursive call for the for the largest node, which is 6, it will be no OP. Actually, we call by the index. Sorry. Like here, the index. It is not. We don't call it recursively by the value of the item, but by the index of the item. Sorry. So the index of 6 was what here? The index of 6 was 7. Yeah. So I will just call it the index by the index of 7. And since it is just a leaf node, then the recursive call of it will be no operation. I'm not going to do anything, and I will continue in my here. So here I started from 3, I will go to 2. So now on 2 I have 5 here. I will go to here, to this side. I'll move to this side, and I will do the same kind of thing. I will compare its children. Does one of its children, it has one of its children is greater than the root? No. So the call of 5 will be no OP, which is no operation. Then from 2, I will go backward or decreasingly, which is when I have 4. And 4, since previously the very first operation was I have it swapped 1 and 6. Now the 4, one of its children, which is the left child, which is 6, it is violating the heap property. Now I will do the swap and I will sift. So after I will swap, here the 6 will get here and the 4 will get here. And now the heap is violating again. So this is why I will call recursively by the value of the previously largest. So the stack frame will be like this. If we try to visualize the stack frame, this is our stack frame. And we have our lovely main sitting there for eternity. Now, first we have called it by what? We have called it, what was the index of, we have we started at I lost counting. We
We started
started
at
at index.
3, which was 1.
Yeah, we started at 3, and 3 was 1, and we did swapping, and we started at 3, index 3. Then index 3, the call of index 3, recursively called index what? Index 3 called what? Index 3, when we were index 3, we call index 6, which was the largest, right?
7.
7, yeah. Index 3 called 7. And since 7 is just a leaf node, so 7 didn't call anyone or anything. So 7 just returned and it popped off the stack. So we need to remove it out of the stack. 7 returned to what? Its return address. It returned to its callee, or sorry, to its caller. And her caller or its caller was 3. It returned to 3 nothing. It hasn't done anything. So 3 also will be popped off the stack. Now we will go from 3 to 2. Now we will call our function heapify by the here I will be 2. Now 2 will be add to the stack. So at 2 until this point, this is so guys, I need someone to keep track with me because I get lost in the middle. So the previous process, we have 6 here, right? And we have 1 here, right? Please correct me if I'm wrong. The previous operations. Now we call heapify by the index of 2. So 2 is added to the stack. So at index 2, I have what? I have 5. And I need to change this 0. So which one I have changed? Here, this one, right? Like the 6 was switched with this one, yeah, with this one. And the one got here, right? So at index 2, we have 5. So 5, we compare its children, left and child. Any of the 2 children violating the heap property? No. So the 2 will be popped off the stack without doing anything. Out. Now my bookkeeping will decrease and it will hold the value of 1. So heapify will be called onto the stack with 1. So at index 1, I have 4, the value 4, right? So 4, it has these 2 children. 6 on the left, 3 on the right. Heap property is violated. Does the heap property violated?
Yes.
Yes. So I need to swap. I need to swap with whom? With the largest. How did I determine the largest? From here. I check if iterable of left index is greater than the presumably largest, then I update the largest. And also I check the iterable at index right is greater than the previously presumed large. And if so, then I did my large. And here I know which one to update, if it is the right or the left. So now 6 at index 3. I need, I will swap 6 and 3. 6 and 4, sorry. So I need to delete this here and delete this. Here I will have my 6, and here I will have my 4. And before swapping, what was the index of the largest item? The index of it was 3, right? So here I will call recursively by the value of 3. So when we'll call recursively heapify with index 3. So now I am in the recursive call. So now I am inside 3. And in 3, what do I have at index 3? Can anyone, guys, if anyone following along and he got the hang of it, can complete this stack frame tracking? Anyone would love to complete this stack frame tracking? Hello, hello.
I mean, I guess at index 3 we have 4. 4 only has 1. 1 is smaller than 4,
Yeah,
then nothing
so
happens.
we'll keep just repeating the same kind of process. So like following recursion is a little bit tedious and is a little bit confusing, and sometimes like if you just lost one teeny tiny thing, you will go into a rabbit hole. So like I just wanted to just to explain to some extent the idea of a stack frame and how to track it. But this example here is very long-winded and we will be spending much more time. But this is the basic idea of it. I hope that you get the idea of it.
I have a question. So in our linked list, right? We also need to check whether the left is I guess smaller than the right, since the order matters in that case. So far we're only comparing with the parent, left and right, but in our list, the order of whether an item should be on the left or on the right also matters. Or doesn't.
Uh,
So for example, in this case, 6 is
in
bigger, or 4 and 3 are smaller than 6, but 4 is bigger than 3. And maybe if it was reversed,
four is
then
so before we swap, you mean? Before we swap, we need to check like
I'm
this
just
is
saying that
this is what
the
we
comparison
need
with
to
the
check
parent is not the only one, maybe?
uh, comparison with the parent. So let's put it on the example here. Uh, Before we swap this, we have here 4 and 6, right? It used to be like this. It used to be like this. And our I is 4. This is I, this is the I, and this is our left, and this is our right. And what we are doing in the code here is checking if I left is less than the size, which is not going beyond the border, and iterable of I left greater than iterable of I large, then I am updating I left. And since that I am comparing also I right, and since if I right is greater, if I right is greater than the new value of I large, then I'm also comparing it with the left. Did you get the idea, Sawa?
I do, but it wasn't my question. But I think the next iteration of the heapify will fix it probably. If we could maybe go through like an example of a tree with like just 3 elements, so we can go through the whole thing. I think that would be useful.
Simulated with tree with only 3 elements. So if we have here, so let's say we have one, no, not one, 5, 7, 8, like this, right?
Yes.
Okay, here we are checking if the left index is not going beyond the border of the overall size of the tree, then and only then I check the value at the left index if it is greater than the value at the root. So this index 0, this is 1, this is 2. Then we copy this, bring it here. So I'm comparing I left, which is 7, is greater than 5. Yes. Then I am updating what? Sorry, I am updating the index of the largest, which is now hold the value 1, right? Right?
Yes.
Large now hold the index 1. Now again, I'm checking, I'm comparing the right value of the new largest, which is at index 1, which is 7. 8 greater than 7, yes. I will update the index of largest to hold the new index of the greatest child, which is 2. Now, on the next iteration, I will update it to 2. Is this was your question?
Okay, now you switch 8 with 5. You have 8 at index 0, 7 at index 1, 5 at index 2. And then what do we do after?
I check if my
I mean,
which
skipping the heap of I since we won't have anything. So going back to the while loop.
yes, going back to the while loop, yeah. Yeah. I really hope this
Well,
will work
uh,
because like
I know
there's something
that
going on.
in the simplified, there's no finance. Hello?
Yes, hello?
Well, so in the simplified function is a recursive function. There's no
Yeah,
way you're putting a return value.
regarding the
Where
recursive
are we going to put the return? Yeah.
regarding the recursive function, this is what we have discussed here in the stack frame. Like we kept track how each element recursively called another element and how they are got popped and add, pop and add until the stack frame is only left with the main, which is presumably not here right now, but it is like virtually.
Yes, but the code, there's no way you put a return function. That a return, that's to break up from the recursion. So where are we returning? At what point are we going to return? Or what is the logic that makes us return out of the heap function, the heapify function? So we don't have an infinite recursive function. That's what I'm asking. Did you get that?
Sorry, sorry. I didn't get you.
I
Okay, if
believe I believe he was asking
okay,
about the return of the heapify, and also begs the question of the condition of
keep a
the
fight. Okay, okay. I think we need to add more comment. So basically, he heapify is a side effect function, which is implicitly return none, but it has a side effect, which is it produces output, but this output is implicit. Like I don't return value out of it, but I mutate my original list. I mutate it. Mutate, which is I change it in place. So basically, Heapify is a side effect which change my heap, which maintain my heap property by changing by swapping swapping nodes if necessary.
So basically, it
This
will
is the
change our
this is
array from merge
the
keyless.
output. Mhm.
Is it gonna change our list from merge keyless? The L
Is it?
underscored LLST is gonna change that one or modify it in place.
Yes, it is going to change. It is going to change it, yeah. Which is LL he list of linked list. LLL stands for like linked list, list of linked list. Like this is the let's rename it. Let's rename it because here this is it should be our flattened list, right? Not the should be our flattened list. So here let's uh, mm, LLST change it by flatten list. It is more obvious now, right? The flattened list, the flattened list. So yeah, it will change our flattened list by doing what? Our goal is to achieve is to reach this point, guys. Where is it? Our goal is to reach this point to have a max heap, which is the biggest item on the root. Then I will swap the root with the last item. Like whenever I reach this point, I have my biggest item on the first index. Now I got my heap property, which is each the root node and the root of each subtree is bigger than its subchildren. So now I will sort it by just swapping here the zero element at zero, which is the root, and we swap the root with the last element. Then when I do the swap, now I will repeat the same process but excluding the ordered element, which is now I have only one ordered element, which is 6. So my new list will start from here, excluding this one. And when I do the same process, I will have my 5 here. Now I will exclude these two and my list will start from here. Like instead of having list of eighth element of size, a list of size 8, I will have list of size 6. And after I get the 4 here, I will have list of size 5. And then I will get the 3 and so on and so forth. I will keep reducing until I reach the end. Heap is empty. My list is sorted. Now I will have a sorted list. Now I will get to the point to adjusting the link. So up to this point, I think the heapify is done. I have heapified, and up to this point, I have built my heap. I build my heap. Now, what is left is the sorting. And for the sorting, what I do is I swap, right? I swap. And when I swap the first element with the last, the first element which is the root. So my I size minus 1 while I greater than or equal 0. I need to do what? I need to swap, right? Yes.
Wouldn't that be
So
just swapping the first element with the last element?
yeah,
Like
yeah. Yes,
heapify
exactly. Yeah,
0 or like flattened less 0 equals
yeah,
minus 1.
yeah. Right. 0 flatten 5. I is 0. I think I missed something here. Yeah. So now I have a swap. Since I have a swap, now I have the 6 here. So I need to reduce my list size. I minus 1. So now I will no longer visit this thing. I will no longer visit it. I will start from here now. So after the swapping, my heap property will be my heap property should have been violated or is violated. So in order to maintain again or to restore the heap property, I just need to self.heapify, and I give it my list, which is flatten list, and I give it the index, which is 0, and the size is I. But there is something missing. I don't know. But let's move on. So here we are sorting our heap. Now we need to do what? We need the link. So by the end of this loop, I will have my flattened list sorted. But the link is a total mess. So I think I need another variable. Okay,
I
my
think
mind
you
just
can
gone blank.
look
My mind
the
just gone
list
blank.
and then point
Come
to the
again?
next element.
Yeah, yes, you are right. So for I just need to look through it for node in LL
I guess we would use
really flat.
the index rather than the node itself to make sure we can access the next one. So if we do, for example, for E in range size, and then
Merged. Go ahead, continue.
so like for E in range of size, and then you link the flattened list E dot next equals linked list or flattened list E plus 1. And you keep going, and the last element it would just point to null.
E. You said E.
So for E in range size,
For E in
or
range.
range size,
In
and
range
then
size. Okay,
flatten
which
list
is the size of
E
our
dot next,
flatten list of I
or I, yeah, equal or
dot
dot
next.
next equals flatten list of I plus 1. But check in, of course, if
List
I is still in range.
Yeah.
Or if I
So
plus 1 is still in range.
okay, flatten of I. Yes, I like the idea. I like it. So I can say temp equal flatten of 0. And here I can say temp uh, temp dot next
Equals flatten list I.
flatten
And in
flatten of
that
I
case, you would
temp
start
temp
with.
temp. Hmm?
In that case, you would start from 1 instead of. So in range 1 size, yeah, exactly.
And since the last one should be So the last next should be null temp dot next equal none, and I should return what?
Latin list 0.
The head.
Flatten this is everything.
Plan list of 0. Plan list of 0. Yeah, plan list of 0, yeah. So here, adjusting the links, and we might run into a case where the list is empty. Like, what if the list was empty? You know what? Let's give it a go.
Yeah, we might need an if guard at the very beginning.
I feel you'll not get it. There's something missing, but I couldn't tell. But let's
There's a
like
double C in class at the very top.
shade invalid. There's double what? Come again?
Double C in the class solutions at the very top. Yeah.
Double C. So not supported between instance. So there's something wrong.
Oh, I believe we should be accessing like
Uh,
the
the
value.
value.
Yeah.
Yeah, you are right. Mm, Here also we should be swapping the value. Like, right? We don't need to swap the whole list. Like, who cares to swap the whole? Like, swapping
And
the
also
the
in line
whole node
54. In line 54.
54.
Yeah.
54 here. Yes, not val. Not val. Let's run it. Swear. Okay, this index out of range. In which case it is out of range. Yeah, since if flatten list equals 0, turn no.
If the length of flatten list equals 1.
Yeah, like I'm just used to Vim and the key binding isn't working and this started to this. So if the length,
And I believe in the example they didn't return none, they returned just an empty list. I'm not sure if they're considering that as none.
okay, is not valid. No, because here in the annotation they say optional of list of node.
Alright,
List
then
node,
I
optional
believe it
list
is
node.
none. None or just nothing at
So
all.
I think yeah, it is none. Yeah, it is none. So where is it?
30 something. 35.
30-ish,
35.
35.
I,
Yeah.
I think you can put a guard, like if the lists
Nice.
equal to empty list or empty list of empty list.
Hello? Come again?
Yeah, I mean if you put a guard in the beginning, if lists equal to empty list or empty list of empty list.
Yeah. This would be
One
nice.
moment.
We'll be saving operation that shouldn't be done. So our guard condition should be up above here.
I think it can be
If
like at
our
the very beginning. You check the like the original list. Yeah. If it is empty
Here,
or
here.
if it is made of
Yeah.
empty lists.
If list
If not
or
list or
len
if not
of
or
len of list of zero, return
if not list.
none, none, yeah, um, equal zero. If len of list equals zero, or len of list of zero equals zero. And let's check it out. So has no len, object of type generic alias has no len.
I guess maybe the first one isn't a list. Yeah, because
Here,
yeah, the first element wouldn't be a list. It would be like a linked list.
yeah. All right, yes. Sorry, I got that. So now list index out of range. We
Can
need
we,
to check
for example,
something.
add if not list or if len to lists?
Uh-huh. If not list of
Lists
like
of
this.
an S. Yeah, maybe.
No, it will be one. If not list
It's
or
still we are reaching something that
if not list zero.
isn't there. But I'm checking here. I'm checking the flatten this the flatten list. But since the list is empty, it should be here. I shouldn't.
I mean, the card is the simple. Both conditions are like equal. The length, if not list, then
I
if
guess
not
so.
list and not list zero.
So I think maybe
Okay.
example 2 and 3, we just need to find something to exclude both of them. And I'm not sure what the example 3's guard would be.
No,
I
if
think we
not
should
lists, if
Yeah,
not
revert
yeah,
lists
I understand that.
revert or
and not list zero.
if not list,
Not list zero
if not list,
and not list zero.
if not list
Lists
or
with this. Yeah. Not list zero.
not list of zero or
Yeah.
not list of zero. Okay.
And as an S at the end. Lists.
Uh, yes. Nice.
Nice, nice.
Okay, now let's cross our finger and hope it works. We got okay, we have a wrong answer for something, which is 121 out of 134.
Oh, because the first
So our
element
condition,
is empty, but the
yeah,
second one is not.
yeah, yes.
Or
So our
maybe we can
condition
use like
here
an any,
will not make sense. Hmm?
either like we check it from there or we check it after the flattening.
After, yeah. Because if we check it here, we will have an extra loop. If we want to check it before everything, we will just have an extra loop. But since I already have a loop that is looping, and for each iteration I'm doing something to the flatten, I can just if my flatten list return on if len. And since len is constant time, so it's nice. No need for extra loop. Like it is not all of one. like I used to think that because we are coming from C background, and in C, if I wanted to get the length of any iterable, I need to go by n times, which is O of n. But in Python, internally, the implementation of len internally, it keeps track of every single item that you add. So whenever you are done with your list, the len is already ahead of time, has information about the length of your list. This is why it is constant time in Python and O of n in C. So len of lan is equal 0, return, right? That was our previous thing, right? Now we have flattened list is not defined. Did you mean
A double T in flattened, yeah.
double T? Yeah.
I think you deleted some of the
3.
stuff. Do Control Z. Go back, go back.
No, it's 3T in
Yeah.
flatten.
Yeah, like this. Like I've deleted everything. I don't know how does this happen. This is why Vim is great, guys. This doesn't happen again. So let's submit it again. Bismillah. Oof. When
Nice.
2 times, and like for memory we have pn 50%, and for the speed, yeah, it is kinda actually. I want to address something you mentioned previously, Sabah. If we gone if we've gone with the min heap, I think we will save sometimes. We will save sometimes
There is
because
also okay, go on.
if we do the min, if we do the min, if we do the min heap here, actually we can do it now. Let me
There's
copy
also
this.
a way, I'm not sure if it's even like considered cheating, but we can just switch the values instead of switching the nodes like you did. So at the end, we wouldn't have
Ye-
that extra loop of linking since they're already linked
Uh,
to each other.
can you elaborate on this?
So we have
So to
a
do what?
list, we have a flattened list. And instead
Yes.
of
Huh?
switching the nodes, we switch only their values. They're already connected to each
Yes.
other. So it's sorting just the values, but the nodes themselves are still connected to each other. I think that's cheating, but maybe.
No, no. I think it is brilliant actually. It
So
is.
we're already doing half of it by in line 64 by switching just the values.
Yeah, we are switching
And
the
we could
value, but
just go all the way with just not, I think if you could print it after it comes from that, I think maybe we can get a sense of if it's like correct or not.
okay. Tell me what do you want me to do? I
So
kind of
maybe
got
after
lost.
the first while or like
After
before
the first
linking,
while loop,
before
this
linking,
is the
or maybe after the second while too. We just print
this
our flattened list.
here. I need to print
Maybe
it here.
after the
I mean,
second, maybe not like outside any
after
while
the
loop.
second, this is
I'm
Can
just
you put
outside.
the code before you
ah yeah,
change
yeah.
it?
Copy the code in the comment.
Okay, copy the code. Yeah, this is our class node definition. So, by the way, guys, I just wanted to mention something, which is شنو ده؟ ما نبي what what is this? From where all of these garbage come from? I've made a GitHub repository that we like that that can contain all of the technical interview and lead code practices. And if anyone, let's say, Sabah decided to go with another approach, like here we have implemented max heap, Sabah implemented min heap, so we can like we can have. Let me show you the GitHub repository and how one can contribute and how we can collaborate on this.
That is a really good idea.
So I already made it. It is called LeetCode. And the idea of it, for each difficulty, we'll have a branch. So the hard one will have a branch on hard branch, the medium on medium, medium problems on medium branch, and easy, and so on and so forth. So for the contribution, you just need to fork the repo, clone it to your local machine, make a pull request. Each problem should be in a separate directory with README file, contains description of the problem, demo, an example, the difficulty level of the problem, the learning objective out of this, the learning objective of solving this problem, and the actual link to the problem on LeetCode. And last but not least, each solution trial should be in a separate file, and please document your solution so that any visitor can track your code easily. Future you is included. Let's enjoy. So let me give you an example. So here, do you remember the Pacific Atlantic one? Like me and some of and my friend Muhammad, because we have a hard time wrapping our head around that problem, we implemented in C, we implemented with BFS, DFS, and such. So this is the folder, the description of the problem. This is the demo. This is 2-dimension and 3-dimension demo. The learning objective of this, we boost our understanding of breadth first search and depth first search. The difficulty was medium, even though it should have been hard. It is not medium at all. And the actual link. And here, these are the file. So here, some have implemented BFS, separate file. Some has even implemented in C. They solve it in C. And here a solution in DFS. So this is a demo of how the contribution should look like. And I think we'll have a place we can refer to whenever that we need to practice something, we need to read about something, like it will be a reference, good reference.
That
So
is
feel free.
amazing. If you could share the link to that in the comments, please.
Yeah. Okay. So instead of so there's someone said like share the code. So instead of sharing the code in Discord, we can have it all on GitHub. And if anyone wants to make a contribution, make optimization, like maybe this is like I'm quite sure our solution here right now, it is not well performant, but we learn as we go. So I think instead of sharing the code on Discord, I will just make I will commit it and push it to GitHub, and then I will share the link to the repository. It will be a nice idea, right?
It is a very nice idea.
Okay, thank you. So this is our solution. We just need to add more comments and documented
I
module
believe
define solution to
we edited it. Oh, okay. No mind, no mind.
okay, solution class, merge sorted linked list and return the head of all list joined in one single linked list. And return the head. So all all linked list will be joined in one single linked list. And that's it, yeah. So this is the flattening, this is the build heap, this is sorting our heap, build our max heap. And here adjusting the links. And I do believe that if anyone got to implement it with min heap, we can get away with the extra loop. Like here, this extra loop, we don't need it if we implemented min heap, because we can do it in one fell swoop, inside this while loop. But for now, I will just leave it as is. So split term get status, get status. So my get hyphen p add merge k list problem. Git push the origin heart. And now if I go to LeetCode on the main, I have only one problem inside this directory. But if I switch to hard branch, I should have seen two problem. Our new merge sorted linked list, and this is the README file. This is the description of the problem you are given, blah blah blah. This is the example, this is the difficulty, and this is the link to the problem. If anyone has no problem to submit, please follow the contribution rule here. And if anyone has any suggestion to the README, please feel free. We want to learn together and advance together and have fun together. So I hope that this is going to be our single source of truth to refer to.
Yeah, this is amazing. Thank you for the initiative.
And thanks to you giving me this great opportunity. It was a pleasure for me. And excuse me if I was not so understandable, or if I haven't gotten to convey any of the concepts as much as it should be. But we can sort it out at any time. So guys, any question? Yeah, I need to share the link. So we can just compare and pull request, but I'll do it later. So we can share the link. Where's the chat? Yeah, here. So is it better to share it here on the chat or on somewhere else?
Okay, we can share it
So,
here on the chat, and then later on we can do an announcement with like explaining what it does and everything.
okay. So this is the repository. And thanks guys for your patience.
All right, thank you.
I'm already past
That was an amazing
software
discussion.
now. Yeah, I really enjoyed. Thank you. Thank you. And
Thank you very much.
it has been a pleasure for me also. A pleasure. See you later, guys.
Good night, everyone.
Good night.